Good morning, everyone. Our lecture today is about statistical quality assurance and how to use quality control charts. To understand the topic today, let's imagine that we are making tablet and we are making quality control test for tablet. We have hardness, friability, disintegration. So for every test, there may be some variation in hardness between one batch to the other, or variation in friability between one batch to the other. For example, if the hardness of one batch, the average hardness or the sampled hardness was like 4, and the other batch is 4.2. So there is a little variation in hardness between this batch and the second batch. This may be a natural or common cause of variation, which is expected to have little variation. But if you have your hardness for many batches between 4 and 4.5, and then you have one batch with hardness 8 or hardness 1.5, which is so far from the 4, hardness 4. So this could be a special or assignable cause of variation. So the job of the statistical process control, which is abbreviated as SPC, is to detect and eliminate any assignable cause of variation. Natural variation or common variation is something expected, but special or assignable causes of variation that we need to detect and avoid or eliminate. To detect the assignable causes of variation and eliminate them, we need to use something called quality control charts. We can make quality control chart for weight variation of tablet or capsule. We can make it for thickness of tablet, for volume of liquid filling. If we have liquid dosage form, we can check if every bottle is filled by the right volume or not. And we can make it if you are making packaging, quality control for packaging step, to detect the number of or fraction of defective blister or strips of tablet. How many tablets or how many blisters having defective tablet, which may not be filled by the tablet or by mistake filled by 2 tablets or not sealed well, so and so on. So we have several quality control charts for several quality control tests. We have mainly 2 classes of quality control chart. Control chart for variables and control chart for attributes. The word variable means that the thing that we are measuring can be expressed by real number, like hardness could be 4 or 5, weight variation, weight could be 100 milligram, 110 could be 90 milligram, so that is variable. While attributes, something like defect in tablet. The tablet or the blister could be defected or not defected. Is it packaged well or right or wrong? It is something which is all or none. We can count the number of defected tablet or defected packages or defected blisters, but we cannot tell that the defect is 90%, defect is 110%. Either it is defected or not defected. That is called attributes. So most of our quality control tests, including hardness, friability, thickness, diameter, weight variation, or almost all are variables except the number of defect in packaging. If we look here down, we can see a sample or a model of quality control chart. You can see that every quality control chart is composed of 3 main lines: upper control limit, lower control limit, and something called control limit. The upper control limit is abbreviated as UCL, lower control limit abbreviated as LCL, and the control limit is called CL. Control limit is not a must to be the average. We have different types, and you will understand what is the control limit and how to calculate the upper and lower in every control chart type. If here the result is here in the x-axis, you have number 1, number 2, number 3, number 4, and so on. This number could be batch number 1, sample taken from batch number 1, sample taken from batch number 2, sample taken from batch number 3. So we are taking different samples from different batches, and we need to know the variation between batches here. Is it something acceptable, or the variation is due to common causes, or this variation is due to assignable causes? If all the points are between the upper control limit and the lower control limit, so here the variation is due to common causes of variation. But if you have any batch outside the control limit, outside the range between upper and lower control limit. So here the variation mostly due to assignable cause of variation. Here we have an alert that we have a problem. We have to check and detect what is the reason of this assignable variation, and we have to eliminate and work on improving our production and make it better. We will take one example for control chart for variable and another example for attributes. So our example for variables will be something called R chart. R is abbreviation for range. Here we need, in every chart, we need to know how to calculate the CL, control limit, the upper control limit, and the lower control limit. CL, UCL, and LCL. The control limit is calculated by something called R bar. Of course, this bar, it means average, and R here, it means range. So we have to calculate the range of our results, the range of our values. And then, of course, we'll understand from the example in the next coming slide. And then we have to multiply this R either by something called D3 or something called D4. D3 and D4 is obtained from this table. So whenever you need to answer or to make R chart, you need this table with you to extract the D3 and D4 values. So to understand, of course, we will go to the next slide, and let's take an example to understand. Here we have 3 samples, sample 1, sample 2, sample 3. Sample 1 is taken from batch 1, sample 2 is taken from the second batch, sample 3 is taken from a third batch. So we have 3 samples from 3 different batch. But what is the sample size here? Sample size here is 4. So we have 4 observation, it means 4 tablets from every batch. We are taking four tablets from the first batch, 4 tablets from the second, and 4 tablets from the third batch. So again, number of samples are 3, taken from 3 different batches. But number of observation, it means the sample size, each sample is composed of 4 tablets. So the sample size is 4. First step is to calculate something called range. Range, it means the maximum value minus the minimum value in every sample. So in sample 1, what is the highest value? The highest value is 16. 16 minus the lowest value here, the lowest value is 15.8. 16 minus 15.8 equal 0.2. So the range of the first sample is 0.2. For the second sample, the maximum value is 16.1 minus 15.8, the lowest value, so the range is 0.3. For the third sample, the maximum value, the highest value is 16, the lowest value is 15.8, so 16 minus 15.8 equal 0.2. So to calculate control limit equal the average of the ranges. So to calculate the average, of course, it will be 0.2 from here plus 0.3 plus 0.2 divided by the number of points, so divided by 3. So the average will be 0.233. That is the R bar or control limit. What is the upper control limit? To calculate the upper control limit, you have to multiply R bar, same number, 0.233, multiplied by D4. How to get D4? D4 from this table. But this table has so many D4 and D3. How to extract the right value? It depends on your sample size. Here it's very important to understand again the difference between number of samples and sample size. We have 3 samples. That is not important now. Here it is written sample size. Sample size, it means how many tablets in every sample, how many observation in every sample. We have 4 tablets in every sample. So sample size here is 4. So for sample size 4, D3 equals 0 and D4 equals 2.28. So to calculate the upper control limit, you have to multiply D4, which is 2.28, by the R, which is 0.233, to get the upper control limit. And to calculate the lower control limit, multiply 0.233, which is R, multiplied by 0, which is D3. So now we have the main elements of the control chart. The control limit is 0.233, upper control limit 0.53, and lower control limit equal 0. Here let's plot the chart. The y-axis is the sample number. So here you have sample number 1 and the range is 0.2. Here you have sample number 2 and the range is 0.3. Here you have sample number 3 and the range is 0.2. You remember 0.2, 0.3, 0.2. That are the values coming from the table that we calculated in the last slide. And the table should have, of course, other sample 5, 6, 7, 8, but just to make it simple, we extract only the first 3 samples. So the data we have can plot only these 3 points. But if you have more sample, you can continue plotting other points. And then you have to determine really where is the upper control limit. So make a dotted line like that. That is the upper. You have to write UCL, upper control limit. It was, I think, 0.53. And the lower control limit is 0, so that you have to write here LCL. And here, that is the control limit. This line in the middle, this black line, is the control limit, which is 0.233. Here it is shifted up, but that is the control limit, which is 0.233. So now all the points are within upper and lower control limit. Lower control limit is 0, upper control limit is above more than 0.5. So all the points of all the batches are between upper and lower control limit. So we can comment here that the variation is due to what? Variation here is due to common causes, not due to assignable causes. So as a quality assurance team here, no need to worry. Yes, we have variation, but all these variation are within the acceptable range. No need to take any action. Then we will have another example, or an example for attributes. Attributes, as we mentioned, that is something which is all or none, and the only example in our field may be the number of defective tablet in packaging. As I mentioned, again, attributes in packaging, we cannot tell that packaging is 90% right, or 10% or 50%. Is it defected or non-defected? Is it right or wrong? There is no number, but we can count the number of defective tablet, but still it is attributes. So here we have to calculate in the C chart. We have control limit, which is C bar, which is mean number of defective tablet, and we will have example now to understand. Here upper control limit is C bar plus 3 square root of C, and lower control limit C minus 3 square root of C. So upper control limit and lower control limit, they have the same equation except the sign only, plus or minus. So the example, as we know, it should be the number of defective tablet are monitored using C chart. Use the data below to make the chart. So we have how many samples? 10 samples. As usual, 10 samples are taken from 10 batches. And from the first batch, we have 3 defective blisters or tablet in packaging. The second batch, we have 2. The third batch, we have 3. Here we have 1, and so on. So in every batch, we are taking samples from the blisters, and we are checking how many blisters are empty. You know that every blister should be filled by a tablet, but for example here that is defected one. There is no tablet inside this blister. So that is, I mean, about number of defective. Okay, so what we shall do now, we have to calculate control limit, which is the average number of defective tablet. What is the total number of defective tablet? 22. So we have to add all this number together and get the total, and then we have to divide by the number, like any average. The total number of defective divided by the number of samples. So 22 divided by 10, so the average number of defective tablet is 2.2. Then the upper control limit, same number is used, 2.2 plus 3 square root of 2.2. The lower control limit, same equation, but it will be 2.2 minus 3 times square root of 2.2. The upper control limit here is 6.65. The lower control limit here is minus 2.25. When you see a minus value or a negative value here, you have to discard it and consider that the lower control limit equals 0. So usually in C charts, the lower control limit you will get negative value. Just discard it and write 0. So again, to understand the chart, here this number is sample number 1, and we have 3 defected tablet. Sample number 2, we have 2. Sample number 3, we have 3, and so on. Sample number 4, we have 1 defected tablet. Even the data in our table are 10 samples only. So it is just a briefed table, but if we have more data, if we have 20 samples, we can continue plotting this part, the right part. So you will do like that. On the x-axis, sample number, and in the y-axis, the number of defected tablet. And then you have to determine the upper control limit. We mentioned it was 6.65. So this line represents the upper control limit. The lower control limit was a negative value, but we considered it 0. So the x-axis itself is the lower control limit. And the control limit, we mentioned it is C plus. This dotted line is the control limit, so you have to write here CL. And then you have to comment if all the points again are between the upper and lower control limit, if all the points are between this range, so that is common cause of variation. So the variation here is due to common cause. But if you have one point outside, for example here or here, any point above the upper control limit, so the variation could be due to assignable cause of variation. Here we have another example of R chart. I will not answer it, I leave it to you to practice, but I just want to tell you that here we have 3 samples, and we have in each sample 5 observations. So the sample size here is 5. So if you want to take the D3 will equal 0 and D4 equal 2.11. So don't think that sample size is a number of samples. Number of samples here is 3, while each sample is having 5 tablets, so the sample size is 5. So you can get D3 and D4 from the table easily. And of course, what you need to do is to calculate the range for sample 1, range for sample 2, and range for sample 3, and to calculate the average range or R bar, average range, and then you need to calculate the upper control limit by multiplying D4 R bar and lower control limit multiplying D3 R bar. After that, at the end, you have to plot the chart and check if all the samples are between the upper control limit and the lower control limit, or there is a sample outside. Even if there is one sample only outside, it means that there is a assignable cause of variation. Here we have an example of C chart. So of course, as usual, C chart is talking about defective tablets in packaging. Here we have 8 samples, and in every sample there are a number of defective tablets. So what we have to do now is to calculate the total. For example, the total is 20. So, and then you need to divide 20 divided by 8. So what you calculate now is C bar, the average. And then you will use the equation, simple equation C bar plus 3 square root of C. And that is the upper control limit. And the lower control limit equals C minus 3 square root of C. Thank you so much, and I hope you understand what I want to tell you.